All right, so I'm still out of breath coming over here from part one, even though it turns out it took me 24 hours to actually get started on part two. So the goal of part two is to talk about the actual implementation of LZW in this old compress tool that was distributed with old Unix versions up until the point at which some patent issues intervened. But it's been a whole day, and now it's Saturday morning when I'm recording this, so obviously this is actually my leisure time, so I have to spend some of this time thinking about my philosophical pursuits. So I guess what we'll think about is this whole theory and practice thing. Obviously people like me spend our leisure time thinking about this, especially if we're stuck inside and there's nothing else to do. And it's been getting to about 25 degrees out lately, so I'm really looking forward to staying inside for that too. So here you have a matrix. And we might know you might have done this actually in first year programming or numerical analysis or something, that we can easily take two n by n matrices and multiply them together with this simple algorithm. We want to be careful about using words like this, but we could call it a naive algorithm, which runs in n cubed time. And just to be clear, the dimension of n is this. So it's the number of rows and the number of columns of the matrix. So it's n cubed with n defined that way. And the great thing about that algorithm is it's really easy to write. We can get first-year students to do it. It's easy for compilers to optimize because it's three nested loops, and there are a lot of benefits to the way that compilers handle loop optimization that can apply to this. And it requires very little extra memory because all we need to do is store a few constant values, a few extra variables. And it's great because if you take a look at code and you see something with three nested loops, it's pretty easy to identify when you're looking at the old-fashioned naive matrix multiplication algorithm. Now the reason I bring it up is that maybe you've heard about this before, but there are algorithms that do better than n cubed, and we might know from our experience working with algorithms that n cubed is a bit scary. We would rather avoid n cubed if we can. And so it turns out that there are algorithms that are faster than that, and one of them is this Coppersmith-Winograd algorithm, which can give us n to the 2.3 approximately, which is pretty good compared to n cubed. Now the reason that I bring it up is that sounds great. We've got this sub-n cubed algorithm. Let's just go use that for all of our matrix multiplication. And yet that naive algorithm seems to persist. And the reason is that the constant factor sitting on top of that Coppersmith-Winograd algorithm on that n to the 2.3 is so massive that the matrices you'd have to have if you wanted to actually see an advantage in real running time are so big that we wouldn't be able to even store them on modern hardware. So I wouldn't be able to actually show you a matrix that can produce an advantage on that algorithm. This is a typical problem that we have, which is in the study of algorithms, we often design algorithms not for the sake of actually implementing them, but for the sake of proving some point, often a point about what the lower bound of some operation is. So we've been able to prove Coppersmith and Winograd, among others, were able to prove that matrix multiplication doesn't actually require n cubed time. But that doesn't mean that we actually benefit in any way practically at the moment from having this algorithm. It does mean, of course, the way that you expect, the way research works, that future researchers might be able to come up with some improvement on that is practical. But we have to be very careful about things like this. And the point I'm trying to make here as it relates to compression is the same thing is true of compression schemes. We've spent a lot of time talking already about this idea that we can have clever compression schemes and we can apparently show amazing results off of some scheme that takes some stream of bytes and then produces a very small stream of bytes, only to realize later that the amount of overhead required to actually store that, so the extra metadata we have to store, completely cancels out any advantage of compression. And so in this case, maybe the issue here is that the quirk that hides the fact this algorithm might be impractical is to do with the fact that we tend to use big O notation for this. The argument I would make is that regardless of what system we use to measure, there likely are loopholes because the system we use will discard certain information as not being germane to whatever we're measuring. There are loopholes in any system, big O or anything else, that could disguise a bad practical solution as apparently a good one. Now, I think big O notation was a great idea for the purposes of Coppersmith and Winograd, but not necessarily for demonstrating that their algorithm is practical on matrices of this size. Just for some more context, so again, because it's Saturday morning for me and I want to be philosophical, there's also questions like, what is the fastest algorithm for some other basic task? And one really basic task, and I love this one, is multiplying two numbers together. So I have two n-bit numbers, and I would like to multiply them together in the fastest time. And we know that that's typically done for us when we're programming. We just use the multiplication operation and don't think more of it. And the reason we can get away with that is that we have hardware that uses some fixed word size, and that it's got operations defined, usually in hardware, so circuitry, that can perform multiplication quickly. But there is the question of, if I have two n-bit numbers, how long does it take to actually perform the multiplication in terms of the number of bits n? And if I use an extremely slow algorithm, so the most basic one might be repeated addition, which isn't done in hardware usually. If I take two n-bit numbers and use repeated addition, strangely, the actual running time ends up being 2 to the n. It turns out, though, that the best algorithm for this, for multiplying two n-bit numbers, in the same vein as Coppersmith and Winograd, requires, curiously, this 1729 dimension Fourier transform. And you can appreciate that if you were a hardware designer, you would probably rather not implement such a thing into hardware. And so it's another example of an algorithm that proves a point theoretically, but doesn't necessarily give us any benefits besides some insight into the complexity of the problem in a practical sense. It's still way better to use old-fashioned techniques to multiply two binary numbers together. It turns out that these examples, the Coppersmith-Winograd algorithm and the 1729 dimension Fourier transform for multiplication, are obviously pretty flippant. They're real examples of this sort of issue. It's actually what's called a galactic algorithm. And that's a term I've learned based on looking this up on Wikipedia. I can show you the Wikipedia page here. So here's the galactic algorithm. And this is a term somebody's coined, and it shows us the example of the 1729 dimensional Fourier transform there. And it also points out that the number of bits you actually need to multiply two numbers together to achieve any real advantage for that is so obscenely massive that we're not likely to see it anytime soon. And you can take a look at this page. The reason I wanted to show the page off is I wanted to show that there was something great hiding at the bottom of it. So it shows some examples. There's the Coppersmith-Winograd algorithm, a galactic algorithm, something, and the reason for the term, I imagine, is that you need such a huge amount of input data. The input size has to be so large, it's on a galactic scale before you get any advantage. We see some problems coming out of graph algorithms. There's that name Claude Shannon, which we'll become quite familiar with later in the course. But buried at the very bottom of this page, this is wonderful. It says, there exists a single algorithm called Hutter search that can solve any well-defined problem in an asymptotically optimal time. And then, of course, the weasel words barring some caveats. So I don't know about the use of the word any if it bars some caveats. But apparently there is some magical panacea that can solve literally any problem in optimal time, but with such a massive constant that it would be, according to Wikipedia, now I don't know who edited this Wikipedia page, never be practical for anything. If that doesn't, assuming that we believe Wikipedia, if that doesn't prove my point, I don't know what does. And so the key here is that just like in the study of algorithms or anything else, we have to be very careful when we talk about compression schemes, that when we talk about one in abstract, so we talked about in part 1 LZW in an abstract sense, we take a stream of symbols and we create a stream of symbols. We have to be very careful when we talk about something in abstract to temper ourselves in terms of how we actually implement that. And it turns out that LZW can be implemented very easily. There's not very much overhead needed, and we're going to see that in the next few minutes. And so we have to be very careful about evaluating compression techniques. And now the theory versus practice thing also shows up in terms of what kind of data do you want to compress. If you're designing a technique that's really clever, but you're not careful about how you evaluate it, you might end up actually having tons of loopholes that make the technique terrible on plenty of pretty common pieces of input data. And so, of course, as I've mentioned before, it's a really big deal to me, and maybe much more of a big deal to me than it is to the authors of the books that we're using, that this course see that issue from both sides. I don't like the idea that a lot of coverage of compression techniques focuses too much on the theoretical algorithm side of things, which I think is really important because that's actually my background, is coming out of the algorithms, the area of algorithms. But I think we also need to, if we're talking about such an applied thing, because we use compression in such an applied way every day, we really need to have some grounding in the way that these schemes actually get implemented and whether they're practical in their implementation. So we're going to get back to talking about LZW. So LZW came out of the mid-'80s, and it was a descendant of a family of algorithms that showed up starting in 1977. And one of the reasons it was great was, and we'll see this as part 2 continues, one of the reasons it was great is that very little metadata is needed. The algorithm itself can be implemented pretty quickly. There's some memory constraints we'll have to impose, but even on 80s era hardware, it was a pretty fast algorithm. It was relatively simple, which meant that a reference implementation was relatively easy to understand by the standards of the time. And so it became part of this Unix compress program. And we traditionally use the .uppercase Z extension for those, the files produced by compress. And what it does is it uses LZW and it stores the symbols produced by LZW first in 9 bits, and then if the symbol table gets too big, it uses 10, then 11, then 12, up to 16. And remember that we can't let the symbol table get grow unboundedly, because whatever computer we're running on will run out of memory eventually. It turns out that LZW is also used in this image format, which I'm going to continue avoiding trying to pronounce. This format's still in use today in a sort of niche market, but it still actually is in regular use. LZW, its popularity waned because the W in LZW is Welch. And Welch, his employer, he was in an industrial R&D position when he invented the LZW variant. His employer had patents on the algorithm, and his employer, the company, was bought by a different company, and the patents changed hands. And eventually, whoever ended up with those patents in I think the early 90s, began trying to enforce them, and they became litigious. And so various pieces of software and Unix distributions that had LZW buried inside of it, then they became sort of nervous about distributing code that included the LZW algorithm because of this patent enforcement. And the actual compress program was a bit of a special case because it's open source. And the way that patents get enforced against open source software is something that's still evolving today, but certainly at the time it was. And so there was a question about whether you could sue some agency for distributing open source code if they weren't profiting off of it. But certainly software developers that were working on for-profit projects didn't want to involve LZW because they didn't want to get tangled up in a patent mess. And that's one of the reasons, besides the fact that an algorithm like deflate has better performance, that algorithms like deflate, which is used in gzip and zip archives and other things, why it began to take over, why it became the dominant algorithm. Now, as I said, deflate does generally give us much better performance, as we saw in part 1, than LZW. But I think that the end of LZW's popularity was hastened by the fact that that developers were nervous about patents. Deflate wasn't encumbered by the same set of patents. That there may have been some patents affecting it, but it doesn't appear as if developers were so nervous about the enforcement of those. They weren't being pursued so litigiously. So I want to talk about specifically what happens if we have generated this LZW symbol stream and we want to store it on disk in a way that we can then recover the results. So a decompressor can then look at it and it can restore the entire original input file. So implementing exactly what's described here, which is a description of the Unix compress tool, with exactly one thing that you're not allowed to do, is assignment 1. And by the time you watch this, I will have posted a write-up for assignment 1. The feature that we're omitting, I would have actually liked to include it. The feature that we're omitting is a special practical enhancement that compress uses, where it can indicate at any time it wants that the decompressor should dump out the entire symbol table and start from scratch. If the symbol table gets too full of junk, then we can dump it out and start again to improve compression. That's something I'm going to call a reset marker. I would like to do that in assignment 1, but we can't because the implementation of reset markers in the compress tool has weird historical bugs that are sort of intractable to resolve. It's very difficult to understand why they work. It's due to weird arithmetic errors going back 30 years. And what's interesting is, and maybe our first example of this, if you're writing a compression tool with a decompressor and you have bugs, so things you weren't expecting, but that don't actually affect whether the program is valid. So it can still compress and decompress, but there are aspects of it that were unexpected to you. If those bugs persist, you have no choice but to leave them in forever. Because once people start using your tool, they compress files, and they expect that decompressor to work, because they might be compressing files for archival reasons. So if you change the decompressor so those files don't decompress, and they try and decompress their backups or something in 5 years, they're not going to be happy. And so as a designer of a compression scheme, you have this problem of if you're not careful and you release the scheme into the wild and there are things in there you didn't expect, you're stuck with them. And so people have noticed this weird bug in the reset marker feature of compress in the last few years. And the people currently maintaining that code have said, well, yeah, but we can't do anything about it because it's stuck. This is a 30-year-old, at this point, I guess it's a feature by default. So we're not going to worry about that for the sake of not having to reverse engineer a strange arithmetic bug that dates back to the 1980s. So we saw in part 1 that if I want to use the old compress tool like I would on our common login server, csc485b.csc.uvic.ca, I would use commands like this. I like piping data in and piping data out. So compress and the decompressor both allow me to do that. I pointed out in part 1 that they're actually, traditionally you'd use this program uncompress. These days, most Unix or Linux distributions I've taken a look at seem to alias that to something else, or it's unpredictable whether they do or not. So for the sake of clarity, we're going to try and always use compress-d instead to make sure we're decompressing with the right tool. Just to be clear, you can run compress and gzip and bzip with a file as an argument, which does something sort of weird. I feel like it's a bit unnatural. I don't like it. But if you give it a file name as an argument, what it does is it tries to give the impression that it's taking that file and compressing it in place. So after you run a command like this, this file suddenly exists and input.txt no longer exists. So it makes it look as if it took input.txt and compressed it in place, even though it actually doesn't. It just makes a new file and deletes the old one. And then if you try and decompress it, it deletes the compressed file and creates the decompressed file. Now, I don't like that because I like being able to keep my files around and I want to decide when they get deleted. So although, for the sake of completeness, I'll point out that you can do it that way, for assignment 1, you are required to accept input by standard input and required to produce output to standard output only. If you add some argument mode, I won't use it. The other thing that's nice about that is that it also gives us an easy way to enforce the streaming requirement. Because if you're allowed to just open files, if I give you the file on disk, then I guess you could skip around in the file. You could read the file once, rewind it, read it again, and that creates a bit of a gray area about what counts as streaming. Whereas if I force you to read from standard input, you sort of have to read it as a stream, or at least if you want to save up the data, you have to put it into your own array in your program, which is really easy for me to notice. So obviously if you do that, I'll catch you, so don't do that. You'll notice in the assignment criteria there is, the marking is affected in some way by whether you can do things in streaming mode. It won't be the end of the world if you can't, but you should aim to do that. In particular because I could try and pipe in a file that's 10 or 10 gigabytes in size or 20 gigabytes in size. In fact, in theory, I could try and pipe in data that isn't actually produced from a file. I could write a program that generates the first 20 billion Fibonacci numbers and then pipe it into your program and expect that your program can work and not run out of memory and not try and save up too much data from the input. So in a sense, piping is a good way of sort of a quiet way of enforcing the streaming requirement. So as we've already seen in the lecture from last Wednesday, we design a compression scheme to perform some sort of transformation of the data that hopefully makes it smaller. And we then try and store it in a representation that we can decompress. Of course, we have to do that or else it's not a valid scheme. And so we like to differentiate between the stream of actual compressed bits that grows proportionally to the size of the input data, more or less, and whatever other data is needed by the decompressor to perform decompression. So maybe I'll call that metadata. Now, it doesn't necessarily have to be the case that metadata is of a constant size. The metadata could also grow proportionally to the input size to some extent. But there is a distinction between the stuff the decompressor needs to get started, the bootstrapping information, and the bit stream of compressed data that it can stream through and decompress byte by byte or block by block, as the case may require. We also saw in part 1 that the output of a particular scheme might not actually be a bunch of bits. It might be something else, and then it's our decision how to encode that into a bit stream. And so what we saw in part 1 was that LZW, as its compressed data stream, produces a bunch of numerical values, and that's it. And it's up to us how to turn those numerical values into bits or whatever other representation we prefer. And we have to do that in this case. The reason we have to use bits or bytes is because we're trying to encode it to a file on disk. So we have to somehow convert it to a format that can be stored on disk, which will require bytes. We're going to get into this part slowly. Assignment 2 will require us to implement a compressor that uses a much more complicated format. We do want to begin talking about the file formats used by compression tools, and consider the fact that they don't always contain just compressed data. They might contain other things because there are other reasons that we design compression tools besides actually achieving compression. Things like gzip and bzip are often used for archiving files, certainly in a compressed format, but we also want to be able to know certain things about those files for when we recover them. So the first thing we tend to see, even in a simple format like the one from this lecture, is a magic number, something at the very beginning of the file, a marker to indicate what kind of a file you're looking at. And that's a good sanity check to make sure that if you're looking at data that it's the format you were expecting. If the magic number isn't what you were expecting to see, then you might have a problem with your file. It's not the file you wanted, it's corrupt or something. It's also nice because if my disk has some sort of integrity problem and I lose my file system structure and I go try and recover blocks of the disk, I could use magic numbers as a way of picking out what I think each block of opaque data actually is. Now, some formats also include things like error detection. So we'll notice later that gzip and bzip both include things like checksums at various points in the file. And the idea there is that you decompress the data, and assuming that the data was error-free, you can then match the checksum of what you decompressed to the checksum already stored in the file. That's not required for compression, but it's a nice thing to have for file archival. Some formats, zip files are a good example of this, contain some indexing information to allow you to go through and pull out only parts of the file. So actually a zip file is, in a sense, several separate compressed streams of data. And the file contains basic file system indexing so that if I only want one file out of my zip file, I can skip through and only pull out that one piece, as opposed to decompressing everything and then sifting through what I get to take out one file. But that indexing information isn't really mandatory, because if I really want to pack the file as tightly as possible, I don't need it. I just pack everything into one contiguous block, and then I unpack it later and sift through it. But it's nice to have because often in zip files, we do want to pull out only a part of the original data. And then a lot of schemes contain a bunch of other stuff, up to and including weird arbitrary text comment fields where you can add whatever you want. But certainly things like creation time or the username of the user that created the file we're compressing, those are often stored because it makes it easier when you decompress to bring the file back to its exact state when you compressed it. So we're eventually going to study, there's a space missing there, we're eventually going to study the .gz format, which does contain a bit more bulky metadata. The format we're going to use today by the old compress tool is really simple. It contains 3 bytes at the beginning of metadata, followed by the compressed bitstream, and that's it. The magic number will be this 16-bit value, and we'll see what that 3rd byte of metadata is in a few minutes. So that brings us back to LZW. We know already that compress is designed to encode anything. In the example here, I'm encoding a bunch of text. But I could encode arbitrary binary data in 8-bit chunks, and that could include every possible 8-bit sequence. So I can't, in my symbol table, I can't define any symbols with indices lower than 256, because those are all used by these single character symbols, which could be anything. And just as I mentioned in part 1, because of the way the decompressor works, even if the compressor can see ahead and notices that nobody ever uses symbol number 6 or something, it's not allowed to recycle it for its own uses because the decompressor doesn't have that knowledge. So the compressor can only use information that it knows the decompressor also has. And so in general, that means every 8-bit sequence could occur. So we provide the compressor with data 1 byte at a time, and then we produce this compressed data stream, which is not a bit stream, it's a bunch of numbers, and we then have to find some way of storing that on disk. And we'll notice that if we can't store each of these numbers separately as an 8-bit value, because there are numbers that show up even pretty early on that can't be stored in 8 bits. It's also worth noting, just like in part 1, that I like to write the compressed data stream this way, with ASCII characters where they're appropriate, but actually, of course, the compressed data stream is a bunch of numbers. And so there's the letter A, there's the space character, and that's what we're working with, and that's what we should expect to always be working with. The use of letters is a visualization trick, whether it's in a slide or anywhere else. In my text editor, displaying characters is just a visualization aid. That's it. Everything is just numerical data. And so this is the same disclaimer as I made in part 1. So in terms of the compressed data stream itself, not the file format, but the compressed data stream, we already saw LZW just produces this. If I provide these numerical values to the decompressor, it can decompress the entire stream. There are some weird kinks that show up in some cases, so that CSCSC problem. But if I provide this to the decompressor, that's all it needs, just that compressed data stream. No other metadata is needed. Now, some metadata will later be needed by the file format, but nothing is needed by the compression scheme itself. That is not the case for all compression schemes. So the question then is, how do I turn this sequence of symbols into a bunch of bits? Keeping in mind that I have to make sure that whatever I do at each step allows the decompressor to follow along. That's the first question. You probably know the answer to this one. Can I just encode each of the individual pieces of this sequence in 8 bits? And the answer is, of course, no, because there are some values in there that need more than 8 bits. Okay, the slide actually says obviously not. So the slide has a bit more of an attitude about this than I do. But for me, the slide was designed on a different day of the week. Here, for me, it's Saturday morning. I'm relaxed. This is my leisure time. For some reason, I'm recording a lecture. So I can't store these symbols in 8 bits apiece. Okay, so why don't we try using 9 bits? Well, we can observe that if we want this scheme to be generally applicable, we want to be able to compress huge files. And for that, if we limit our symbol indices to 9 bits, we get 512 indices. And we know that the first 256 of them are already eaten up by single characters. So we have to start, as we can see here, at index 256. So if we choose to use only ever 9 bits, then we only get 256 extra symbols. And you'll notice that after a sequence of only this amount of text, I've already gotten through almost, just under 20 symbols. And so I don't necessarily want to limit myself to 9 bits. The problem is, if I use a larger number of bits, I might be wasting space early on, when I do only need 9 bits. At this point, with this compressed data, I can store every symbol index in 9 bits. And so there's a question of, I want some flexibility to have as many symbols as I want, up to some reasonable limit, but I also don't want to waste space where I know I don't need it. So the decompressor and the compressor, with this sequence of data early on, before the symbol table has filled up, they both can agree that we do not need 10 bits, we only need 9. And it's worth considering that the way that LZW works, the abstract version of LZW from part 1, the symbol table just keeps growing. The more data I feed in, the more symbols I end up with. And so the slides use a specific example here, but you could think any number could be thrown in here. If the data is long enough, I could end up with any number of symbols in the symbol table. Something interesting to think about for later, and not too much later, somewhere around, I think, early June. Maybe by then you should have thought about this, but is to think about if we know LZW is pretty deterministic, and there's no real choices it can make, so there's no variance between different compressors. I know the symbol table starts at 256 for this example, after these single character symbols. How long will it take at minimum? So what's the shortest input you could provide that would populate, so actually put a symbol at index 300. We don't actually have to use that symbol. It doesn't have to appear in my compressed data stream, but it has to be put into the symbol table. So that's one thing to think about, to reason about that kind of thing. Now on exam, if this topic were to come up, we probably wouldn't worry about the full 8-bit set of characters. As I mentioned in part 1, we might talk instead about, suppose we only have 4 valid characters, A, B, C, and D, so 0, 1, 2, and 3, and then make similar statements about that. So we have to choose some number of bits, and we can't have an unbounded table size because obviously we can't choose an unbounded number of bits for one thing, but also because our computer has a finite amount of memory, main memory, and it may be the case that the files we compress are far larger than anything we could store in main memory. And one example is, well, maybe I'm compressing a 10 gigabyte file on disk, and I don't have 10 gigabytes of memory, perhaps. But also, maybe I'm doing streaming compression. Maybe I'm taking a video stream that I am just generating dynamically, so security camera footage or something, and I am continuously streaming it for years on end through an LZW stream. Well, I don't know why I would use LZW for that, but I may never actually be storing the result on disk. So I'm not limited by, in terms of the size of my compressed data stream, by any limit on the amount of memory I have. But I need to store the entire symbol table in memory. So I have to impose some limit on how big that symbol table can get, based on the amount of memory I think is reasonable to consume. Now, it turns out that that limit's been imposed for us by the compress tool, which is one reason why we're implementing that tool and not making up our own, because we want to learn how to live with other people's design decisions to some extent. It's worth considering that when that tool was designed, it was on late 80s, early 90s era technology by the end. So the decision they made about the memory limit is a great deal lower than whatever decision we might make today. And you might notice when we talk about other schemes later that the more modern schemes in some cases aren't terribly more advanced than previous schemes, but they've defined built-in memory limits to be much higher. So LZMA is well known to consume huge amounts of memory and CPU on its highest settings, because LZMA is a newer scheme that was designed in the age of large amounts of memory and CPU being available, where people didn't mind letting compression take hours and hours on end, and they had processors that could process what would have previously taken days or weeks in only hours of processing time. This parenthetical is what I just said. So here's my idea. Let's cap the symbol table size at 2 to the 16, so 65,000 give or take. This is the limit imposed by the Unix compress tool. We should observe that that's 65K, and we could 65,000 entries, each of which might be more than 1 byte. We could easily use 2 to the 20 or 2 to the 24. We could even, if we really wanted to push things, go up to 2 to the 30 on most machines without creating too much trouble. But we're going to stick with this limit. You can maybe agree when you're listening to this that it doesn't really matter what limit we choose. We need some limit. So this input contains 30 bytes. And when I'm done compressing it, I have used 275 entries of the symbol table, and we know that we can store that number, 275, in 9 bits. If I use 16 bits for each symbol in my compressed data stream here, would I really be helping myself at all? And the answer is no, because I have all these symbols I now have to store in 16 bits, and if you look at them, you can see that a huge number of the bits in each case are eaten up by zeros, and that's sort of a waste of space, because both compressor and decompressor know that those first few bits, those first 7 bits in all cases, are going to be a 0 bit, so why store them? So there is this issue of I can set the symbol table size at most 2 to the 16, which means I need at most 16 bits. But there are times in the algorithm where both compressor and decompressor can agree they do not need 16 bits. So the compress tool is aware of this, and it is able to use a more progressive scheme where we know in advance how many bits we need to represent a symbol because both compressor and decompressor have the symbol table. They both know this symbol table ends at a 9-bit number. And so they can both agree to only use the number of bits at each step needed to store the indices that are currently available in the symbol table. And so this slide agrees with that. So if I were to limit the symbol table size globally at 512, then I could just use 9 bits. But I don't want to do that. I want to have the option of going over 512. The key here, just to emphasize what I said a minute ago, is that we need to make sure the decompressor is able to understand the decision made by the compressor at each step. But because they both have the symbol table, anything that uses the symbol table, we can assume both sides, compressor and decompressor, have that information. So what we could do is we could then say, let's not use any more bits than we need until the very first entry of the symbol table that needs the larger number of bits has been generated. If our symbol table has 512 or fewer entries, which means we're using indices 0 through 511, then we can store that number in 9 bits. And we may actually never use symbol table entry 511 or symbol table entry 256, but we know how big our symbol table is at each step, and so does the decompressor. And so if compressor and decompressor both have a symbol table with 512 or fewer entries, then they'll use 9 bits. But as soon as we store our 513th entry, so that would be entry at index 512, then both compressor and decompressor will begin using 10 bits. Because at that point, there's a possibility, once there is something in index 513, there's a possibility we might need it. Even if we never need it, we may. So we have to read the number of bits that could be used to store that value. So the protocol used by the compress program is pretty simple. We start with using 9 bits per symbol. And then over time, we add more and more things to the symbol table. And at some step in the future, we will add something to this index, 2 to the num bits. So in this case, if we start with num bits equals 9, we will eventually store something at index 512. At the end of that step, after we have stored that thing into the symbol table, because we know during that step we would never use the index because we've just created the index. After that step, at the end of the step where we add that entry, we're at the first point where that entry could have, indeed be used. It could be that at the very next step we need entry 512. So at the end of that step, start working with a larger number of bits. So if we start with 9 bits and we fill entry 2 to the 9 in the table, then after that step we begin reading 10 bits per symbol. Once we get to 16 bits, we stop because we can't make the symbol table any bigger than 2 to the 16 by an arbitrary implementation-dependent limit that the compressed implementation has decided will be 16 bits. And I'll show some pseudocode in a few minutes that describes how we handle that case, because maybe you can see that LZW, as one of its core features, fills symbol table entries constantly. So what happens if we force it never to fill a symbol table entry? So I can develop that a bit. There is some pseudocode that addresses that. So what I want to demonstrate here is why we want that reset marker feature that we're ultimately not going to be allowed to use in assignment 1, which is that if we cap the symbol table size, and this is only true if we cap the size, with the basic abstract LZW, where the symbol table could grow unboundedly, this is never going to be a problem. But if we cap the symbol table size, we run into the following issue. So suppose I'm trying to encode a string of text consisting of every word in English in alphabetical order. So I have up here the A's, but this list goes on for maybe thousands and thousands of entries. So I have up here the A's and I encode them. And I run through the entire thing, and I've already used up just under 20 entries of my symbol table. And we notice that there is a propensity for those entries to have A's in them in a lot of places. In particular, things like space A tend to show up quite a bit because obviously we're looking at a list of words separated by spaces where we start with a bunch of words with A at the beginning. So I have all these symbols involving A, and therefore my early symbol table entries will be filled in with a lot of patterns that occur in the A words in English, including the letter A a lot, but also any other letters that tend to occur in A words. And the issue here is that by the time we get down to words starting in the letter P or the letter Q, these entries are still in the table. And we've added lots of other entries, but maybe our table is maxed out. Maybe by the time we get to the letter M, our table is full and we can't increase its size any further. And we could argue that some of these patterns, maybe this one, I don't know, maybe this one here, might still be useful. Lots of words end in the letter K. They might still be useful later, but a lot of them, especially ones like this, are not going to be as useful going forward. And as time goes by, the likelihood that an old symbol will be used again tends to decrease in a very intuitive sense. I don't want to try and get into that in terms of statistics. I want to argue for the time being, in the way that the old compressed program did, that we can agree that if our list of words is sorted alphabetically, we're not going to see space A very often after our list gets through the A's, because every other word we see will start with some other letter. And so over time, the older symbols become less useful. Now in LZW, abstractly, that makes no difference, because over time we add more and more symbols, and the more recent symbols tend to get used more. The issue is that in this compressed implementation, where the symbol table size is capped, at some point the symbol table fills up and never changes again. And if it fills up around, let's say, the letter M, then for the letter P and the letter Q, any patterns that exist in those words never end up in the symbol table. And the symbols from A and B and C might be stale and used very little by then. And so compression performance will degrade over time once the symbol table fills up. Now, the way that the compressed program handles this is it includes a special symbol that it can issue, that it can emit, where if that symbol is ever seen in the stream, then the decompressor and the compressor both dump out the entire symbol table and start the LZW process from scratch, which means if the symbol table got stale, then we can just start over and create fresh symbols. Now, the way that this works is the compressed program has what's called a reset marker symbol. And if that symbol is ever used, the compressed program will then stop. It will then clear its symbol table and start again. The decompressor, as soon as it sees that symbol in the stream, will clear its symbol table and start again. But the issue here is that the reset only occurs if that symbol shows up. So when to place that symbol in the stream is a choice of the compressor. It could do it frequently, it could never do it at all. And the way we're going to handle this issue is we are never going to do it at all. So we're never going to reset our symbol tables, again, because of some weird bugs in the way that that symbol actually works. The way that the compress tool tends to do that in practice is it keeps an eye, as it works through the file, it keeps an eye on how good the compression has been so far. So how many bytes it's saving with things like symbol substitutions. If it notices that that number drops below some threshold, then it decides the symbol table must have gotten stale, and it throws out the symbol table with a reset marker, and it starts over again. So the way that the compress handles this is it says that its base alphabet won't just be all of the 8-bit symbols, 0 through 255. It actually adds an extra base symbol with index 256, and that's the reset marker. So if the number 256 ever shows up in the stream, the decompressor will treat that as a reset and clear the symbol table. So what that means is that you're not allowed to use index 256 anymore, because that's now actually taken by a single character symbol. Now you're not allowed to use that symbol either. You can't use the reset symbol in assignment 1. But what that means you have to do, and it's a pretty easy adjustment, is your symbol table has to start at 257. You have to leave that one entry clear so that the decompressor doesn't get confused, because you're going to be using the same decompressor that is used for the regular compress tool. So that's the only thing you have to do as an adjustment. Don't try and use reset markers, but make sure that your first real symbol index for an LZW substitution symbol is 257, not 256. And I'm already looking forward to getting a couple of emails from people that may have skipped through this part of the lecture asking, why doesn't my code work? It seems to work correctly. I have LZW working, but the decompressor doesn't handle it. It might just be that you forgot to include an entry for that reset marker. And just to clarify again, if the reset marker isn't in the output stream, we still need to reserve a symbol for it, but nothing will happen. Until the decompressor sees the reset marker, it doesn't reset anything. So if we just ignore the reset marker and never put it in our output stream, the decompressor will have no trouble. And just to be clear, it's already bold, but don't include reset markers in your implementation for assignment 1. And then whether you use them or not, you still have to make room for them in the symbol table. So what that means is leave an entry of your symbol table blank for the reset marker at index 256 and start your actual LZW symbol table with the new symbols at 257. Just for the sake of completeness, it turns out there actually is a way to turn off reset markers in the Bitstream. And the reason that I've chosen not to use that for this assignment is that on shorter inputs, the old compress tool doesn't use reset markers. It doesn't use them until the input gets pretty big because it doesn't need them until the symbol table is full. But the issue is, by default, the compress tool turns them on. And so if you use a bitstream where they're turned off, your bitstream won't look like the one from the compress tool. Whereas if you use a bitstream where they're turned on and you never use them, then your output will be identical in byte for byte to the old compress tool, at least for the first few bytes. So if we turn them on but don't use them, it actually does make it easier, in my mind at least, to do debugging, because it means you can compare your program's output to the compress tool. So that's the reason we're in this weird limbo halfway between using reset markers and not using them. So then the question is, how do we fit those things together? In particular, how does that issue with the max bits constraint work? And I have some pseudocode here. This pseudocode, from an algorithm standpoint, this is your assignment 1 solution. Your job in assignment 1 is to implement this in C or C++, and then to solve our next issue, which is how do we take the resulting set of symbols and turn them into a sequence of bits? So for the time being, I'll observe at this point, here is where we take care of increasing the number of bits that we're using at the end of the step when we fill the symbol table entry 2 to the num bits. And then here is where we handle that case that we fall into once the symbol table is full, where we no longer add new entries to the symbol table. Beyond that, the actual logic in there isn't terribly exciting, so I won't cover that in much more detail. And whether it's exciting or not, it's right there in the pseudocode. So the question I want to deal with now is, how do we turn this sequence of symbols into bits? And it turns out this is a matter of personal taste, and we don't have the option of using our own personal taste here because the decision has been made for us. So we know already that the size of each symbol in bits increases over time. So we use 9 bits at first, we eventually move up to 10, then 11, all the way up to 16, and then we stop. That's great because it means that for the first few characters, we only need the bare minimum of 9 bits. And then later, as time goes by, we may need more and more bits. And that means that short inputs like this don't have some penalty imposed by using a larger number of bits. But the thing is, we now have this issue of we've got these 9-bit fragments, and we have to turn them into 8-bit pieces to store them in a file. So our files are byte-oriented, and even this single symbol A, which is 9 bits long, we have to think of some way of splitting that up into 8-bit pieces. Now, what you might be thinking, what I wanted to think coming into designing an assignment like this is, well, that sounds easy. That's not going to be a hard, issue. What I'll do is I sort of have a stream of bits that goes like this, and then through this row here, and then through this row here. So what I'll do is I'll chop off the first 8 bits of the first symbol, and that's my first byte. And then I'll chop off the next 8 bits, so that's up to here, and then that's my next byte. Well, great. That's my way of handling it, but it may not be everybody else's. And one issue we're going to discover that makes assignments 1 and 2 pretty tough is that whether or not the choices made by other people of the way the bitstream works are rational, it's really hard to get into their head. It's really hard to have the same mindset they do. Even if they've actually made better choices than you would make, it's really hard to believe their choices. So here is what happens. We first take our sequence of symbols, and I've drawn boxes around the binary representation of each symbol. We take our sequence of symbols and represent them in binary. And in these representations, the binary encoding I am using is the one you would have seen from earlier courses where we write the most significant bit first. So we do that. We now have this sequence of bits. And as I said, you and me both might think, well, that's easy. I just take those bits and then I chop off 8-bit chunks and I store those into bytes. This is great. Lecture over. I can go enjoy my Saturday now, right? No, wrong, obviously not. We have to spend a bunch of time talking through exactly what happens to these bits before they end up in a file. And we don't have much historical perspective as to why these weird decisions got made. So the first thing that we do is we take our set of symbols, we convert everything to binary. Okay, I'm following so far. And then we take those binary representations and we reverse the bit order. So just to be clear, what that means is that each symbol's least significant bit now comes first. And you can see that, okay, there is this school of thought that seems to say that least significant bits should come first in certain cases. You might be tempted to think of the term little endian here, although little endian is a term that generally is used to refer to byte ordering, not bit ordering. We don't generally have a well-defined convention for the order of bits inside of a byte because we tend to store bytes atomically. But the word little endian, in a sort of an abstract sense, could apply to this sort of thing. So we take our sequence of 9-bit symbols, we reverse the bit order, then we have this stream of bits. And in the stream of bits, the least significant bit of each symbol comes first, then all the other bits of that symbol in ascending order up to most significant bit, then the next symbol, and so on. So this is, in a sense, the real compressed bit stream, the raw stream of bits that we're working with. The problem is we still haven't resolved how to turn that into a bunch of 8-bit chunks for storage. And you can see, ominously, there's this huge amount of white space left in the slide. So step 3 probably ain't the last one. Okay, so the next thing we do is we chop that bit stream into 8-bit chunks. Okay, so the first 8 bits are the first 8 bits of the bit stream, the next 8 bits are the next 8 bits of the bit stream, and so on. And you might notice, in this case, because my input was relatively short, over here is the very last few bits of the bit stream, and there's only 5 of them. And we know that that is not a byte. That is 5 bits, not 8 bits. So the next step is we have to pad, if necessary, the last bit to be a full byte. So now we have, the number of bits we have should now be a multiple of 8. We have to pad it at this point because the zeros have to go here and not in front of these. In this case, actually, it's symmetric. But we need to make sure the zeros are added at this point, and we pad out with zeros until we have a multiple of 8 bits. And then, for some reason, as if this wasn't enough, maybe whoever designed this changed their mind at the last minute about this least significant versus most significant thing. For some reason, we then reverse the bit order again. So now we have, this is the most significant bit of the byte, and this is the least significant bit. And then we have our final encoded set of bytes. So the first encoded byte of this bit stream is 0x41, then 0x40, 30, 09, 42, 04. So the question then is, what the hell is going on? the slide even says that it's obvious. The slide's been using the word obvious a lot today. Why is this so convoluted? Okay, well, I'm on the internet and people could be watching thousands of years from now, so I better say this is my opinion, but try disagreeing with this. There's no accounting for taste. I have no idea why they chose to encode it this way. I have a feeling that there might be some good reasons that whoever did this had, but those reasons might not be as relevant now because maybe it had to do with the way that the hardware they were using worked. The issue is they made this choice and they have to live with it, and so does everybody else that uses the format. So it could be that whoever wrote the code sat down and thought about this at length and determined that for whatever reason this was a good representation. For hardware reasons, because it made their code easier to write, fair enough. It could also be that they didn't think about it at all. It could be that they were writing some C code to implement their compressor. They wrote a few functions to take bits and output them, and they didn't think about it. When they wrote the decompressor, they basically wrote the inverse of each function and still didn't think about it. Maybe it didn't become apparent to them for years that this was the sequence of steps they were actually following. And the reason that I think of it that way is, first, that does excuse the logic of whoever this was. I've written plenty of code that didn't really make any sense, but it seemed to work, and maybe I didn't revisit it because I didn't realize it would become a big deal later. I'm still paying the price for that in some cases years later. I've written lots of code that people still send me emails about that's maybe no good. The way I would handle this is I wouldn't necessarily make a list in this form where I have all of these steps. Probably what I would do is I would say, well, I've got the symbol 65. What do I do with it? Well, I'll take each bit of that representation and push it into my output bit stream. Maybe the designer of this code said when they pushed the bits of the symbol into the bit stream, they started by pushing the least significant bit. So that's why it ends up here. Then the second least significant bit, and so on. So maybe they didn't explicitly think to themselves, I'm reversing the bit order. Maybe it was just that for whatever reason, the first bit they worked with was always the least significant bit. And similarly, maybe when they decided to take that bit stream and bunch it up into bytes for output, maybe they did the same thing. The issue, of course, is that there's no real documentation of this, and once they made that decision, they were stuck with it. And that's an issue with designing a scheme like this, is that once you've made these decisions and your scheme is out there, you can't change them even if you want to. Now, one thing, I don't know if this is a saving grace or not. So you're looking at this and saying this makes no sense. Or some of you are looking at this and saying this makes perfect sense. So maybe there is accounting for taste, maybe there isn't accounting for taste. Your mileage may vary. It's worth considering that unfortunately this problem is going to come back on us over and over again. gzip and the deflate format tend to use a very similar way of handling bits and bytes that this one does. Whether that's a coincidence or not, I don't know. bzip uses sort of the opposite. So you might notice in this case, the least significant bit has some significance in terms of coming first in many parts of the representation. In bzip, it's always the most significant bit. And that I've implemented both gzip and bzip, and I found that both of them are sort of annoying in this sense because it's hard to in a doctrinaire sense, always keep one bit on one side of the fence when you're representing things. So every format has this problem. Somebody's made a decision of how to turn a bit stream into bytes, and different designers might make different decisions. You might find that on assignments 1 and 2, this is the most annoying thing. On assignment 3, you'll be given wide latitude to make your own decisions, and therefore it may well be easier to encode a bit stream on assignment 3, which will be a more complicated application, only because you get to make the decisions and you get to make things consistent with your own conceptual model in your head of how things are supposed to work. And then this is pointing out, yeah, we don't know if this was a good decision in terms of, well-reasoned and thought out, or whether it was just an arbitrary one that nobody ever thought of that turned out to maybe not be good, or maybe it was good, who knows. It's also true, as another opinion, it's also true that it appears that even formats that have gone through a very rigorous standardization process, so JPEG is an example, they still use weird bit encodings that don't seem to make very much sense, that maybe the people that designed them would have regretted years later, who knows. And so it is really a case of the personal taste of designers, as well as specifically what they're trying to get out of it. And even with big standardized schemes, there's often this tendency that it doesn't matter if the rules are irrational. As long as they can write them into a standards document, there's nothing inherently wrong with having a complicated set of rules, as long as they can find some way of encoding them into the document. And later in the course, we're going to studiously avoid ever having to read the JPEG standards document, because it is no fun. So we have this bit stream now. That thing on the previous slide, this sequence of bytes from the sequence of bits right above, that is our encoded set of bytes. And the question then is, how do we stick that into a file? So we're almost there. Well, that bit from the previous slide is this thing, the bitstream. And on disk, we have our bitstream preceded by exactly 3 bytes of metadata. And those 3 bytes are a way of identifying the file format with our magic number and a mode byte to resolve a couple of variations in the scheme. Now, fortunately for us, the mode byte will be specified entirely by the assignment. So today we're going to go through a specific mode byte we're going to use, and everybody has to use it. There's no room for variation. And it's true that this format, the .z format that this describes, is an extremely basic example, but an example nonetheless of a container format. So a way of packaging up data such that somebody else who's decompressing it can both recognize the format and operate on the format in some way. And so the magic number for .z files is 0x1f 0x9d. And the mode byte is 8 bits long. And just to be clear, because we've had some confusion about this recently, this is the most significant bit and this is the least significant bit. And the most significant bit is 0 or 1 based on whether reset markers are enabled. So there is a way of disabling reset markers. Now, for some consistency reasons, I've decided that in this assignment we will leave them turned on, we'll just never use them. So for our purposes, the reset marker bit will always be 1. The last 5 bits, the least significant 5 bits of the mode byte, are a 5-bit value telling the decompressor how many bits you use at most. So you don't actually have to use this number. So even if you only ever use 9 bits, this is the total number of bits you would use at most for symbol table entries. And you'll notice it's a 5-bit value, which sort of implies you could use 31 here, but it turns out the decompressor will reject anything greater than 16. So for your assignment, you will always encode the number 16 here. Whether you use 16 or not, you will always put 16. Now the other 2 bits, these are don't care bits. They don't have any meaning. They're reserved for future use. I doubt they're ever going to get used. I've been waiting 35 years and they still haven't been used. So we'll set them to 0 because that's a best practice. We have don't care bits. We'll set the don't care bits to 0. And that means we actually have now fully specified our mode byte. It is now 0x90. And so that means the first 3 bytes of our files we produce in assignment 1 are now dictated. They are dictated by the decisions we've just made and by that magic number. And so what we can use is some command line utilities to take a look at this. So here I have a text file that contains 5 bytes. There they are. The hexdump utility is a great utility to use for this. And you can see that hexdump, if you use the -c option, emits things in 3 columns. The first column, this one, is the address of each byte. Second column is the hex values of each byte, and over here the third column is an attempt to render each byte as an ASCII character. In cases where they are not ASCII characters, you usually get dots. So this file contains the 5 bytes that we were working with before, and I try compressing it here, and I put the result in encoded.z, and then I try dumping out with hexdump encoded.z, that's here. And I see 0x1f9d, that would be our magic number, then 90, which is our mode byte, and then 41, 40, 39, 42, 4. And if I go back to my slide earlier, we might observe that I have 41, 40, 39, 42, and 4. So I'm seeing exactly what I expected after this weird convoluted sequence of steps to convert my symbols to bytes. And then, just for completeness, I should make sure that if I decompress it with compress-d, that I do end up with exactly what I had earlier. And so the slide is now observing, as maybe you already figured out, that hexdump is a useful tool. I want to do a quick example of using this on the command line live. So let's do this. So I have here in this directory this file called alaska.txt. It's the longer form of that example that is shown on the slide. And it contains these things. I'm opening it up in an editor here. And I want to observe that as far as I can tell, I'm pressing the down arrow over and over again here. In Vim, I think I've got 1 line of text with these characters. And I want to point out that we're going to use hexdump a lot to look at our compressed output. But I want to point out that it's really important to also take a look at our input in binary. So first I'm going to run hexdump-c and I'm going to pipe that in. And I want to point out that Okay, so these three characters here, 0x41 is the decimal value 65, and we can see that's uppercase A, but we can also see that there's this other character here, and I don't remember putting in some other character. 0x0A would be decimal 10, which turns out to be a new line. So Vim, by default, puts new lines at the end of all of its files, whether you ask it to or not. Now, that's fair enough. I mean, who cares? You can encode new lines just like anything else. But remember that if you're looking at your compressed output, you should be prepared to see these extra characters in there. So you should be aware of that your editor might add extra things. It could get a lot worse. So I've had cases where I paste text into a file from, let's say, a browser window or something else, and it ends up pasting in weird Unicode stuff. So I think I'm pasting in 5 characters, and I end up getting 7 bytes of data. So be aware of that. We should be using hexdump to look at our raw input, not just our raw output. And then let's try running this through compress. And I can then run hexdump-c to take a look at that. And you can observe we still have our 0x1f90 and then 0x90. And then 4140, 300942, the first few bytes of the smaller example that's in the slides. The remainder diverges because, of course, the example is much longer. I also, at the very end here, I would like to put in a quick plug for this option, which is often you don't want to keep making files because you're just testing out a feature. If you're writing your own program, maybe what you do is you pipe the input data into compress, and then you just pipe the result right into hexdump, which makes it way easier to look at the binary output if you're debugging or something without having to dump it into a file first. So this is, I think you now have enough to start on the assignment. The theoretical stuff we're going to cover in the next week is not necessarily too relevant to the assignment, so you can, it shouldn't be necessary. Both this stuff, these 2 parts, and that theoretical stuff does factor into the first exam that we have, so you'll want to get around to that eventually. I'd say probably get around to that assignment first.